So let us do the simulation for the IV characteristics of the MOSFET using Tanner tools. So before you do the simulation, let us have some discussion on the tools which are provided by the different vendors. So these are the different vendors which are like competitors in the market. National Instruments, which provides the multi-sim tool, and a Mentor Office, which provides picture schematic in the Linux version, SEdit, TSpice, and WEdit, which are comes under the Tanner tools in the Windows version, and custom compiler provided by Synopsys tool, and a Virtuoso provided by the Cadence tool. So one thing common is whatever the tools I have given a list over here, multisim might be, and picture schematic might be, and custom compiler and Virtuoso. These all are similar kind of tools, schematic editor tools, on which if the circuit diagram is given and doing the connections on the schematic editor and doing the simulation, the similar kind of process will be done on every tool which is provided now, which is shown here. So all are schematic editor tools, and now we are going to do the simulation for the IV characteristics of the MOSFET using Tanner tools. These are the list of the tools which comes under the Tanner tool will be used. So SEdit tool, on which we do the schematic design, whatever the IV characteristics of the MOSFET schematic I will draw over here on the SEdit, and I will generate a spice code, and using TSpice I will be adding some comments to do the simulation, and after I get the simulation results I will be verifying the simulation results on WEdit. So these are the list of tools which comes under the Tanner EDA that I will be using over here to identify the characteristics of the MOSFET. And one thing I have to highlight across the Tanner tools is we already used the same task, the characteristics of the MOSFET, common source amplifier design of the MOSFET. We studied in the last semester using the multi-sim, doing the simulation that and all. But here, using the Tanner tool, we can have an advantage is it is a technology dependent. We wanted to change the technology, we wanted to add a latest technology, the transistor with the size of 45 nanometer, latest of technology of 45. There are like advanced technology nodes also available, but now we'll be adding a 45 nanometer technology, and we'll be doing the simulation how the transistor with the size of 45 is going to be simulated, and the characteristics how we'll get it, that's what we verify on the Tanner tools now. So before go with the Tanner tools, we should know like how to do the installation for the Tanner tools. That's what we discussed in the last session. And after we do the installation in the system, there are like SEdit icon is created on the desktop, or else we can go with the start menu search. There in the start menu search, we can search with the SEdit, so that once you search with SEdit, you can see this kind of icon. You have to click on that, so that you can see that there will be a schematic editor tool with this kind of navigator, it will be opened. So once you see SEdit navigator, it will be having all these panels. If for suppose any one of the panel is not visible, right, if it is closed, default panel is looking like this, and using whatever the options visible over here, through which we have to know how to do the simulation. So now first of all what I do is there with the view option, click on view. So there is a option that library navigator, so that whatever the panel which is closed we can reopen it. And in the similar fashion, whatever the other panels required, property panels, if it is required, you can click on the properties, so that we can reopen the panel. So these are the panels which frequently used. Library panel is important, and the properties panel also important. So now using file options, remaining options over here, it is not we will discuss one by one with flow of like designing. And now we'll go with the file. There mainly we need to know about like three options. One is new option, another one is import option, and the export option. So first of all, let me go with the new, where I will be creating a new design. New design is where under one design itself we have to create all the schematics. For suppose you wanted to create a IV characteristics of the MOSFET as one circuit, and CMOS inverter as a second circuit, CMOS NAND gate third circuit, CMOS NOR gate as a fourth circuit. Like that, if we have four circuits with you, all four circuits we have to design under one design. We should not create multiple designs. So the design which we are trying to create, under which we have to create a multiple schematics, that we are creating now. So that is what new design. Yes, this name of the design, right, it should be common for all the schematics which we are trying to create throughout the semester. So the design name is I prefer Ganesh is the name of the design underscore 452, my roll number for suppose. Now I wanted to create a one folder in the D drive. I will be creating a folder in the D drive. So I will be creating a folder in the D drive, VLSL lab. Yes, this is the folder I create. In that folder, in the folder with the name of Ganesh underscore 452, my project is created. Just give OK. So this is the my project. We call it as a library, where I'll create four schematics. All four schematics I have to create under this library. Yes, this is called user defined library. That is what user creating four schematics under this library. Yes, so we don't have any schematics as of now. So once you create a schematic for the CMOS inverter, it can be shown over here. It can be visible over here, and NAND gate, it also will be visible over here. Like throughout the semester, whatever the files you have created, all files will be visible over here once you select your project or your library. Now to create a schematic for the IV characteristics of the MOSFET, what I do is the transistors are required, so I will be going with the options add. There like we have to give select, and we have to select the folder where we have installed the tools, dana tools there I have installed, and we have to select examples, and we have to select Tana tools, and there like a process and a generic 250 nanometer technology. There we have all the components, whether like we have devices you need, and analog library where like few components will be there. Every component will be there across like the different libraries, right? We have to select each and every library. So devices library, I will select it and just give it OK, open. So give OK. So automatically this is the standard library will be added with a generic library over here. And in the devices library, what we can see is that multiple MOS transistors will be visible and capacitors are visible. Some components are visible. When you have a schematic, we are creating a cell where you need MOS transistor. We have to pick the MOS transistor. We have to instance them into the schematic. So like that, whatever the components you need, the components where it is available, that kind of libraries you have to add it to the standard user library which you have created. So now what I do is I will be going with the browse. I will be changing that. I will be going with other options also. IO pads. I select IO pads and open. Give OK. So like that, all things are visible, right? We can add the rest of the libraries also. And now what I do is, you have library and we have rest of the libraries also, generic libraries also, right? So now to the library, you have to select the library. Now I will be creating my cell, that you give it a new view of the cell, and the name of the cell is IV characteristics, means I have to use the same name, IV characteristics of MOS transistor. We have to remember one thing, whatever the cell you are creating now, it should be created with the view of schematic, because like we are trying to create a schematic view for the design, right? uh, and it should be there under the design, which is the name of your project. Ganesh underscore 452 is the project we have created, so that's where like the design name also should be there. For suppose if you have mistakenly selected some other thing that devices over here, this is the library you have selected, and you have created the cell with the schematic name. You have created a schematic with this name, then you able to create a cell 0 as a schematic that will be loaded into the devices, right? But what we need is, this is what my standard library, right? Where to that library we have to create a cell, right? The cell name is, again I wanted to write it, I have to write it again, IV characteristics of MOSFET, and we have to select like schematic for sure, give OK. So automatically schematic will be opened, schematic window will be opened. There is option like minus and plus, you can use it so as to zoom it and zoom out. Yes, so now what I do is, onto the schematic window, schematic editor. So whatever the schematic you need, that schematic you have to make it. So I need like transistor along with the 2 voltage sources. So it will be like this. I need a transistor along with the 2 voltage sources. I need it, where the voltage I will be changing as a VGS, that I will be putting on the x-axis. The variation of the VGS corresponding the current, it will be observed on the drain current on the y-axis, so that I will be observing the characteristics. The same thing I have to do it. For that, the same circuit I have to draw over there on the schematic window. Yes, so transistor I will be observing, I will be finding over there in the devices, which I have shown in already. NMOS, we have to select NMOS, because like I have to draw the characteristics of the NMOS transistor, and there we have to use these options over here, arrow marks, so that the multiple NMOS transistors which are available under the NMOS will be shown over here. So one NMOS transistor with a gate terminal is open, sorry, body terminal is open, and another one is body terminal with default it is connected to the ground. So that is your wish. So I'll just refer this MOS transistor, I'll just use instance, I'll take that NMOS transistor over here onto the schematic. Just I'll give one click, so that particular transistor will fit onto the schematic. Then I'll give the escape, or else I'll use like a done option, so that multiple transistors will not come onto the schematic. Otherwise, how many times you give the click, that many transistor will be placed on the schematic. For suppose if I give the instance, if I use one click, so that one more transistor will be fit onto the schematic. I use like another click, that many transistors will fit onto the schematic. Until use like escape, that many transistors will be instantiated. That many couple of transistors will come into the schematic. Otherwise, like we have to use like done options. With that it will be done. I'll give done or escape. There any option we can use it. So now what I do is, I have multiple transistors now on the schematic. There you can delete one by one, or else like we have an option like Control Z, so that it will go to the previous state. So it will come to the previous state, where in first case only we instantiated one transistor. That one transistor schematic will be shown. Yes, so one transistor is taken onto the schematic window. Now along with the transistor I need voltage sources. I just take a ground, I just use instance, I keep that instance of ground over here, and spice elements, I have voltage source across the spice elements, I'll just instance, and where that changes I have to change it there itself. Interface AC, I have to change it to the DC, because I have to keep DC voltage sources there. And with the name of instance is GS, I will be using GS, right? Because name of that name of the voltage source which I am trying to instance, with the name of GS, I will be keeping it over here. For suppose you are not able to change the properties over there while you are instantiating, there is option like we can select that. Across the properties also you can change. The master view AC, interface view is AC, that you can change it to the DC. and the value also you can change it, the name also you can change it. The name I wanted to give it GS, because the voltage source which I'm trying to keep it, that between the gate terminal to the source terminal. So the name of the voltage source which I'm trying to trying to instance over here, it is the name of GS. And there I have to go with the instance once again. I have to keep that instance once again on this one. Or else there is another option, you can copy it and paste it for 2 times. I'll paste it for 2 times. Now I select that one, I'll be changing the name of that particular component. Name of the component DS. I'll change the name of the component DS. So I'll be keeping the ground. I'll just copy and do the paste. Ctrl C, Ctrl V, and minus and plus so that I can zoom it. And I'll use the wire option over here. Here to here, I'll just give one click to initiate the wire and give the double clicks to terminate the wire. Right. Escape. So one thing you have to remember is the cursor is in a normal mode with no notation. Once you select this one, the cursor is changed to the notation of mode. The mode of the cursor is changed, wiring mode. So the notation of the cursor is changed when it is in going into the wiring mode. And I have to select this one. One click so that the wire will be instantiated, and one click to bend the wire, and one click to terminate the wire. Yes, so this is how I do the connection between the drain terminal to the voltage source of DS. And here to here one click and give another click so that the wiring will between that source terminal to the ground. One click, another click, one click, another click, one click. I just copy this ground as it is. I'll paste it here. Yes, another click. So this is how my circuit connections that I have as per the circuit diagram. Right, I have done the connections. After that, for giving a proper notation, whatever the wires that I have, I will be giving the name of this wire, the connection between like a gate terminal and the voltage source. I will be prefer the name of this one as net label lab gate, and I'll do the same thing. I'll prefer this net label as a drain. Yes. So this is how I do the connections. So from this point to this point, whatever the wire, it is visible with the name of the gate. So here to here with the name of the drain. So we call this wire as a drain wire, and this we call as a gate wire. That is how the notation of the wire with the label name is provided. So after you have done the connections, give save, and there is a interface you have to select open tSpice. You can select open tSpice so that schematic file, it will be converted into the tSpice file. So we can able to see the gate level netlist circuit into the spice code. Yes, so this is the spice code that you can see it. So if you see the spice code over here, spice code over here, spice code over here. So whatever the three components we have it, one component, second component, three components, we have three lines over here. First component is a MOS transistor, right? which is connected between the drain wire. So this is the drain wire, and also connected between the gate wire. This is the gate wire, and it's also connected between the ground and ground. So whatever the four terminals that MOS transistor is having, the four terminals, how it is connected between that each and every node that is notated here. So there is a drain terminal is connected to the drain node, and gate terminal is connected to the gate node, and source terminal is connected to the ground, and body is also connected to the ground. So that is how the uh, the nodes notations of a MOS transistor, that is gate level netlist for the MOS transistor. And after that the NMOS transistor, how it has to work exactly, has to work, that will be shown as a model name for the MOS transistor, uh, and with the width of this much, length of this much, and the remaining parameters will be mentioned over here, and that will be the first component. In the similar fashion, we have multiple components. There is another component which we have a drain to source, DS is the name of the voltage source which we preferred. So DS is the voltage source, right? With the notation of V, it will be generated. So voltage source with the name of DS, which is connected between the drain wire, and ground. So these are the two nodes, like a drain node or drain wire and ground. In between that, the voltage source is created. So in the similar fashion, is with the strength of the 5 voltage, and in the similar fashion, there is a GS is the voltage source, GS is the voltage source, V is the notation, directly it will be added. Even though you give the name of the GS is the voltage source. That voltage source is like notation of like adding the V over there. So voltage source with the name of VGS, right, which is created between the gate wire or gate node to the ground. So to the ground with the strength of the 5 voltage. So this is called a spice netlist for the design circuit. So here I will write it like a design circuit spice code, right? So design circuit spice code, right? So one thing we have to remember across this one is, once again, the NMOS transistor is connected between these terminals, which will be doing the function as it is, which is given over there with the name of NMOS. So but the functions, as we know, like C programming, where we call the functions, but if the function is not like definition for the function is not provided to the tool, then it cannot do. So here what I do is that the functionality of the NMOS as a library file, or as a model file, I will be providing over here. So I will be providing over here. There I will be using like options over here. This is the option over here, insert command option over here. If I use insert command, so there is an option like files. You can include files, and there is an option like a browse. So whatever the model files which is required to simulate the NMOS transistor, we have to include the model file. Unless the model file is added over here, that NMOS transistor will not be defined with the functionality. So even though it is connected between these three terminals, so NMOS transistor is connected between the three terminals, it will not do the function, because like we are not including the model files with the name of NMOS. Yes, so now what we do is we have to download the model files. This is the link provided in the description. You can use the link, and through the link, not only through this link, like there are like multiple websites where they are providing the model files. So here you can see these are the model files available for the 45 nanometer technology and 7 nanometer FinFET technology also. Later on we will use this one. So now go with the 45 nanometer technology, click on that, so that we can download the model files of 45 nanometer technology. Means like 45 length of the transistors all will be downloaded now. So already downloaded, let us download once again. Yes, I'll download now. So it is downloaded in the downloads. Yes, so or else like I'll use that yes, downloaded, right? So I'll just unzip them. them. So here those are extracted. So P005, this is the model files, I have it over there. So what I do is NMOS model file will be available over here. Give right click, open with the notepad, open with the notepad. There dot model NMOS. So the model file with the name of the NMOS have the description over here. So these are like all parameters. Based on the values of parameters, NMOS transistor will work. Right. So now what I do is, to avoid the confusion, my model name which is given with the NMOS, I'll be changing with the NMOS 123. So I'll save it. So I'll save it. Give OK. So now this is the model file for the NMOS transistor. Means like the functionality of the NMOS transistor will be defined over here in the model file. NMOS VTL underscore FF. Right. Right, what I do is, so to do the functionality of the NMOS transistor across the terminals, what I do is I have to add the model file over there. So as already given, right, the model name 123. So once like the NMOS 123, this is what the model name, right, the model name where across the model file, that we have to call it over here. Once you keep it over here, so let me use that control M, so that command wizard will be opened, or else like you can open the command wizard through this one also. Open the command wizard, and there is an option like files, there is an option like includes, and there is a browse option. We have to browse the files which is there in the downloads, and over here you have to select like all files over here, and here it was modified, right. This is the file I just have to include, open, and insert command. So automatically this insert command says that we able to add this NMOS transistor model file over here. So whatever the name you changed it, the same name you have to use it over here, unless the model name is not same with the model name in the model file, so it cannot be working over there with the same name. Yes, so now NMOS transistor will be connected between these four terminals, will be doing the functionality as per the model name it is defined over here. So the same name is there in that file, so that it will do the calling over there. The functionality will be defined as it is, that as per the functionality it will do the operation, the MOS transistor will work, right. But what we do is that all parameters already defined, I'll remove them, and the transistor which we are trying to define over here in the model file is 45 nanometer technology. So here the length of the transistor which we invoke over there is 250 nanometer technology. I'll change it to 45, and the width also I'll change it to 45. So, and one more thing, that whatever the voltage sources which are connecting, the voltage sources which are connecting, so here that voltage sources which I have connected, so one is with the name of VGS, this is one voltage source, another one is VDS. So here this is NMOS transistor 45 nanometer technology transistor 45. So here I have to give 1 volt, 45 nanometer technology transistor will be supplied with 1 volt maximum. So that's why like I will be giving 1 volt over here, and I will be giving a 1 volt over here, the voltage source with the strength of 1 volt, and here also with the strength of 1 volt. So there is an option that the DC strength of that particular voltage source I will be changing to the 1, and here also I will change it to the 1. Yes. So as of now the circuit design is done, and the functionality of the transistor it is defined over there in the model file, which is also included. Now what I do is I will be doing the simulation. So simulation point of view, let us see something over there, what kind of simulation I'm trying to perform and what kind of waveforms I'm trying to observe over here. It is there are like multiple ways I'll do the simulation. In the first case, in the first case uh, in the first case I will be changing the VGS over there on the x-axis, and the corresponding ID change I will be observing on the y-axis. It means, it means, it means, so that VDS I will be keeping it as a constant. VDS I will be keeping it as a constant, and I've only changed that VGS. So I will be keeping this one as a constant. Right. So as it says that two variables, So one variable is VGS, another one variable is ID. So with respect to VGS change, I will be observing that ID change. That graph I will be observing it as this one, right? So this we call it as transfer characteristics. This we call it as a transfer characteristics. So now these characteristics will extract over there. For that what I do is I have to do the DC analysis over there, the x-axis where I have to do the DC analysis. So let me use that control M in the sense we can open that command wizard. And what kind of analysis I told, that DC analysis. So DC transfer sweep is to select the DC transfer sweep, and I have to sweep the parameter. Which parameter I have to sweep? The VGS parameter I have to sweep, that which is observed on the x-axis. VGS is the parameter I have to sweep. So I have to sweep the source of the VGS, the VGS voltage source. So I have to select that source VGS from. So I just change that VGS from 0 voltage to, so the maximum voltage I keep it is 1 volt. So I will be changing to the 1 volt. So with the step size of, this is the step size of 0.01. So the same thing I'll mention it over here. 0 is the start voltage, 1 is the stop voltage, increment is 0.01. And now accept it and insert command. So automatically the command is generated over here. So it will do the function as it is as per the command which we insert. So now whatever the command we insert over there, with that it will sweep the voltage of VGS from 0 to 1 volt, so that x-axis will be plotted. The corresponding y-axis we have to plot it. So for that what I do is I will be going with the same option over here, and I will be observing the output where like I have to observe the output. For the changes of VGS I have to observe that as a output, right? Output, what output? DC result output I have to observe, right there. Instead of output as a voltage, I want like output as a current. So current by the terminal we have to select, and whatever the device we have selected, what device, the drain terminal current. So here the drain terminal current. So here the drain terminal current. So this is the drain terminal current. ID I have to plot it on the y-axis. ID I have to plot on the y-axis. Which ID? The drain terminal current of this MOS transistor. So now if you observe that the MOS transistor name is this one. The MOS transistor name is this one. MOS underscore 1. So this MOS transistor drain current, we have to select a drain current. So this MOS transistor drain current. So once again observe that the current by the terminal of the drain of MOS 1. So this transistor. So once you give the add, so automatically this current value will be inserted over there. So now what it do is, sorry, previous command was not in, like it was removed. Analysis. Okay, previous command was erased, so let me use that same thing. Let me do it once again. Analysis, DC transfer sweep, parameter is VGS, source type VGS with the start value 0, stop value 1, 0.01, accept, insert. Yes. So now see, so this is what the analysis, we have designed the circuit, and now we will be doing the analysis. The circuit analysis I am trying to do it. So where the circuit analysis will be doing over here in two steps. In the first step we are defining the x-axis. X-axis is nothing but we just change from the 0 to 1. We just change from the 0 to 1 with the step of 0.01. So that will be the x-axis definition, and we will be defining the y-axis. We want to print the DC value of ID. So DC value of the ID as a output on the y-axis. So x value and y value, if it is defined, the corresponding plot will be observed over there after you do the simulation. So now let me do the simulation, run. Yes, this is how you can see that the characteristics of transistor, MOS transistor. This is called transfer characteristics of the MOS transistor, right? So now, right, whatever the MOS transistor IV characteristics where the transfer characteristics observed. In the second case, what I do is I will be observing the output characteristics. For getting the output characteristics, what I do is the x-axis over there it is VDS. Now I'll change that VDS. I will not change that VGS. I will make that VGS is constant. I will make this constant. I will be changing this parameter. So now there is no need of so here this is what simulation results we can see it, and behind that we can see that code which we wrote it. So for that, right, this is like two layers, this layer and behind that we have a actual layer on which we have a code. So what I do is like a two windows which we have one on another. So we have to select windows. We have to use like a tile vertically so that two windows will be coming one by one. Like one is at left and another one is right. So behind that window will come to the right so that where we write a code, we know we have a code. So what I do is, so this is what I told that the x-axis definition over here, the DC value of the source VGS need to be sweep from 0 to 1. So now I don't want to sweep that VGS where I need like a transfer characteristics. For that I need a VGS change. But when you go with the output characteristics, I have to change that VGS as VDS. So VDS. So that VDS now I change it from the 0 to 0 to 1 volt with the step size of 0.01, so that I will be observing that the same ID change for the change of VDS. I will be getting the transfer characteristics like this. So let me observe the transfer characteristics. Let me close this window. I don't want to save. Let me open this window again. So where just to do the change, only the one thing VGS change I will be changing it as VDS change, and drain current again I wanted to monitor on the y-axis. So nothing have much change, only that VGS in place of the VGS I change it to the VDS, and I'll do the save and I'll just run it once again. So yes, so this is how like we can get a transfer characteristic, sorry, output characteristics, where like a VDS on the y-axis, VDS on the x-axis, the corresponding current ID on the y-axis. So this is how, right, transfer characteristics and output characteristics are plotted through Tanner tools. So now whatever the analysis we have done it, a brief conclusion for this analysis is, so where actually we have three parameters VGS and VDS and the ID. These are the three variables, three variables. So now out of these three variables, only what we did, we have done the analysis for the two variables. So what is the variable? That VGS is the one variable and ID is the one variable. The changes of the VGS corresponding changes of the ID. So one variable and second variable. Two variable analysis we have done it in the first case. In the second case, I am not considering that VGS as a variable. I made it as a constant. I have considered the VDS as a variable. This is the first variable and this is the second variable. So here, so this is the independent variable. This is the dependent variable. Yes. So independent variable, when it is changed as a VDS on the x-axis, dependent variable it is changed on the y-axis. So like that I can say there are like two variables are there while you do the simulation in the first two cases. Now in the next case, what I am trying to do is I will be using the three variables in the sense as like a VDS change. I wanted to change that VGS also, means I will be changing the VDS on the x-axis as it is, and I will be monitoring the drain current on the y-axis. This is the first variable, right, which is called independent variable, main independent variable. This is what a dependent variable. So now what I am trying to do is independent variable I will be putting into the consideration, right? What I do is I will be changing the VGS also, right? VGS also. Previously this one is changed when it is, this one is constant, this one is changed when this one is constant. Now in this case what I do is I will be changing the VGS as well as VDS. VGS is changed along with the VDS also is changed, right? So now what kind of simulation I will be getting is, so for one VGS I will be getting the curve, this kind of curve I will be getting it over here. For the multiple VGS, there is another VGS, I will be getting this curve. For another VGS I will be getting another curve. So like that I will be getting a multiple graphs when I use like a 3 variable simulation. So for that let me close this one, previous simulation over here, don't save, right? So let me do one thing, I'll close this one also, I'll make it big, right? So over here whatever the command that I have, this command says only source of VDS also, only the source of VDS itself changed. Now I'll be making it as a comment line, as in the Verilog code comment line, in the sense backslash 2 times, but now control star, sorry, shift star. Yes, so when you use like star, the particular line will be going into the comment line, so it will be neglected. Yes, now where at this line I'll be using control M, so that I wanted to insert a new command that says two variables need to be changed. How it can be done, let us see that analysis. Once again I will be doing the DC sweep analysis. Previously one parameter was swept, now we will be going with the second parameter also. So first parameter is, right, the voltage source, right, VDS with the value of start 0, stop 1 and increment with the 0.01, right. What it says is I wanted to sweep the main independent variable VDS itself, right? That's what I'm trying to sweep it, accept. And now I'll be using a sweep variable, another one also. There I wanted to sweep VGS also. Now I will be go with the next level of the sweep parameter. Then click over there and use that another source over here. That source name is VGS with the start value 0.5 and the stop 1, increment 0.1, means it will be changed from 0.5 to 1 with the increment of 0.1, so that 0.5, 0.6, 0.7, 0.8 and 0.9 and 1. So like that it will be changed for 5 times with the strength of 0.1 in each case, right? Accept and insert command, close. So now the previous command and this command, the difference over there with the previous one and this one is, so this command will be as it is up to this extent, right? It says that the VDS itself should be changed. Now there is another sweep parameter I will be adding over here. There is a source of VGS from the strength of 0.5 to 1. It changes with the increment value of 0.1. 0.5 to 1 with the increment of 0.1, right? So like that there it will change for 5 times. For every value of increment, the graph of ID should be plotted. So now let us simulate it, right? Here I have to click so that simulation will be started. So we can see that multiple graphs. Yes, this is how I will be getting a multiple graphs. So what these multiple graphs are saying is, if you keep your cursor over there, it will show that this graph belongs to when the VGS is equal to 500 milli, means like 0.5. So when you can close this one, or else like we have a windows and tile windows, so that you can see that code what you wrote. So what you wrote the code, you wrote the code like there is a VGS of 0.5 to 1. So 0.5, this one is 0.5. Yes, this one is 0.6, this one is 0.7, this one is 0.8, 0.9 and 1. So like that we have multiple graphs, so where we can see this is what a main independent variable. So this is the dependent variable, secondary dependent variable. So let me draw this one once again. So here one key point that we have to remember is there are like three variables. One is VDS, another one is VGS, another one is ID. Three variables that we have it. Yes, three variables we have it. So here it is the main independent variable. So here it is secondary independent variable. So this is what a dependent variable. Right. So now what I wanted to do is where dependent variable with the changes of the main independent variable, right? So I will eliminate this one. I will be bringing that VGS on the x-axis. For that what I do is I will be observing at one point. So when VDS equal to 0.5 volts, when the VDS, I don't want to change the VDS further. I will keep that VDS equal to 0.5 and I will be observing the value of the drain current at VDS equal to 0.5 while changing the VGS. So for that what I do is I'll close this one. I'll write the code once again. There I'll use Ctrl M so that the command wizard will be opened. There I have a measurement options. I will measure the DC analysis. When I do it, I will measure the result. I want like a drain current, drain I, right? So the find when the x value equal to what is the x value? So x value is equal to 0.5. So x value is equal to 0.5 means like drain voltage is equal to 0.5. So it means like we are restricting the changes of the VDS to the one point of 0.5 VDS value. So I will change that. I will keep that x value equal to 0.5. There is no chance that the x can be moved from this point to this point. Means like the variable over here it is changed as a constant. Yes, means like a three variables over here. I will change it to the two variable once again, right? So I will remove this variable and the dependence of this one I wanted to highlight. Yes, so 0.5, the value of the signal. What value of the signal I want? What value of the signal I want? The value of the drain current signal. This one, drain current signal. Already I wrote like a ID of MN MOS underscore 1. So this signal I want, right? When I made like a x value equal to 0. So means I wanted to calculate that drain current, find value of the drain current. I wanted to find the value of the drain current, right? When that VD is equal to 0.5 means when you make it as a 0.5. So I will be observing the drain current once again. So I will keep the insert, close it, right? So here it is saying that I will be measuring the drain current, drain I, right? Every time, right? Drain current I will be finding at a 0.5. So once I do it run. Yes, so here you can see the VGS now it becoming a main variable. So here, so VDS was the main variable. Now what happening? I will be extracting a new graph. So on new graph, what happening? So there is a x-axis is VGS and and y-axis is the drain current. Y-axis is drain current and drain current. So what it shows is So the value of VDS is restricted, not like a sweeping from this value to this value. Drain value is like a 0.5. So at 0.5, what will be the drain current? It is the value of the drain current is around like a 5 micro, and for this one the value is like 15 micro. It is around like a 20 micro. It is around like a 35 micro. Like that, multiple values of the drain current, when the VDS is equal to constant. So that values will be plotted over here. There is a value of this much when the VGS equal to 0.5, when the VGS is equal to 0.6, when the value is 0.7, when the value is 0.8, 0.9. It is 1. Means like the second independent variable, now it is brought onto the x-axis. The corresponding changes of the VGS, it is observed as a ID. The current values will be observed over here. So this is how I will be getting a graph. Means when you change that voltage of the gate, the drain current is increased. Yes, the same thing graph says, right? When the VGS is increased, drain current also increased. That will be noted over there with the graph. As voltage of the voltage of the gate 0.5 to 1 voltage it is changed, the corresponding changes of the voltage will be shown on the x-axis, and the current across the drain it will be shown on the y-axis. So only one conclusion from this one is, where I have two variables, one is the main independent variable, second independent variable, and one dependent variable. There is a one option that we have, it is using measurement options. What I can do is, secondary variable I can make it as a main variable, and main variable I can eliminate, so that I can bring the dependency of the ID on VGS. So this is the new plot where frequently used in the observation of the gate property. So as with the gate property of the MOS transistor is, as gate voltage increases, the drain current also increases. So because like it is a voltage control current device, voltage increases, the current is increased. So we able to bring that property into the picture. We can conclude that property. And now coming to the two variables and one parameter. So for that what I do is, last case. So here what I'm trying to do is, same characteristics I will be identifying over here. I will be changing the VDS on the x-axis and the ID on the y-axis, but I don't want to sweep the VGS. Second variable I don't want to include. I want like a one parameter. I wanted to include the parameter. So here what I do is that one VGS I will be keeping. This is what when VGS is equal to constant, I will get it a plot. The ID change we can observe for the VDS change. That is okay, right? So I don't want to change this parameter. Only I have this variable change, and I will be making this one as a constant. Now the parameter of the transistor W I will be bringing into the picture. So one parameter over here, and two variables in the sense VDS is the one variable, main independent variable, and ID is the one variable. So first variable, second variable, and third variable I will be eliminating. So I don't want third variable. I will be keeping this variable as a constant, and now the one parameter W I will be bringing into the picture. So now two variables and one parameter. With that I am trying to do the simulation. Yes. So for that what I do is, so here the width of the transistor, which is constant, now I will be making it as a parameter, right? Width of the transistor I will be taken as a one parameter W, and here I will be giving the notation of the parameter. So I will be giving the notation of the parameter param. So W is equal to, W1 is equal to 45 nano I am trying to define. So now W1 is taken as a one parameter, and I will be assigning the value of that W1 equal to 45. So now that parameter I am trying to sweep it now. So this is the third case. So this command also I will be keep it as a comment line, right? So now what I do is I use Control M. I'll use the analysis once again, right? This is sweep analysis. One variable it will be as it is. So here that voltage source I will be sweep from the, so VDS from 0 to 1 with the step size of 0.01, right? So because we wanted to do the X sweep is as it is, so whatever we do previously we do the same thing, we have done the previously, we have to do the same thing except now second sweep previously second sweep was I have selected the source, VGS was swept, but now I have to sweep the parameter now. So what parameter? W1 is the parameter I have defined over here with the start value 45 nano to 90 90 nano with the step size of 10 nano, right? So now accept and insert command. Yes. So now the difference between the first command is only the VDS change itself observed. In the second one is VDS change when VGS also parallelly simultaneously change. And in the third one, right, it was one variable and another variable and another variable. Three variable simulation was observed previously. Now what I do is one variable and a second variable, two variable along with the one parameter, right? So now let us do the simulation of that one, right? Let us do run, let us do run. Yes, so here if I keep this one, W1 is equal to 45 nano and W1 is equal to 55 nano, W1 is equal to 65 nano, W1 is equal to 75 nano, W1 is equal to 85 nano. It means when you increase the W, here it is, when you increase the W, so the W value increases, the drain current over here also increased. This is what constant VGS, right, for W is equal to 45 nano. So once I increase the W value, automatically ID value is also increased. This is how for 55 nano. So when I go with 65 nano, it will be like this. For 75 nano, it will be like this. For 85 nano, it will be like this. So that the level of the drain current will be increased with increasing the width of the transistor. So that is what the graphs we able to observe over here. For the different width of the transistor, that drain current is also increased. So here it is the graph when you increase the width, right? So what I have done is the width is the secondary variable. I eliminate this one, I will be bringing the width on the x-axis. So now there will be a width on the x-axis and ID on the y-axis. As I said, width increases the drain current increases. So like that width increases the drain current increases. This kind of plot we have to identify at what width the current will be, what that we can observe over here. So now it says that when you keep width of the transistor is 65, the corresponding that drain current will be the 65 micro. So now my question is, so when the transistor is given like this, where I need that the drain voltage is given as 0.5 voltage, 0.5 voltage, I fix it that 0.5 voltage, and what width we have to keep it so that the drain current will be 90 82 micro. So 82 micro I wanted to flow across the transistor. I keep 0.5 or else I keep 0.4 volts, let us suppose, right? So now when I keep 0.4, when I need a 42 micro, right, what is the width we have to keep it? That is what my question. So when you need that kind of solution, what I do is I'll close this one, I close this one, I'll write the code once again. I'll close this one also, where you can see that the script again, netlist over here it is again. So what you said, when the x value is equal to 0.5, right? But you gave x value is equal to 0.4, in the sense I have to change it. So I have to change it. So where I have to change it, 0.4 means at a 0.4 I want to get the values of ID for the different values of width. So now I have to change it to the 0.4, means the drain voltage is 0.4, right? I need uh, a simulation once again. That simulation says the simulation says when the drain voltage is fixed with the value of 0.4. So you said like a 0.4 is the voltage like you are trying to fix, drain voltage is 0.4, and you want the width value for the current of this much. You expect the current of this much, you need the width how much is required. Yes, so here the simulation results will easily says that you expect the current how much, around like 82 micro you are expecting, right? 82 micro you are expecting, 82 micro in the sense somewhere over here, right? Somewhere over here in the sense you have to make sure that the width of the transistor you have to keep it around 85 micro, 85 nano, so that the corresponding current how much you are expecting it will be coming, right? So this is how like changing the different variables and different parameters and different level of simulations we can do it for the multi transistor MOSFET, and where in the complex design where like let's suppose you have multiple transistor, this is one transistor, and there is another transistor, there is a driver circuit of this much. For this circuit it need to pump the current around 82 micro, let us suppose. You have to know what kind of the voltage you have to generate over here, it like 0.4 let us suppose. So you should know the sizing for the transistor, W value how much you have to keep it. So where to identify the W value in the complex circuit design, right? You have to like do this kind of simulation. So keeping that 0.4 and doing the sweep analysis for this transistor, so that you will be identifying the transistor current of this much for the value of W how much across the dependency of the W on drain current on the W. So this graph easily will give the conclusion that where you need the complex circuit design analysis, where the W value sizing and for the complex circuit design everything will be made very easy, right? When you do this kind of simulation, when you know this kind of simulation.